Students, we are going to start lecture number 19, and this is in continuation of the last lecture, that is on mechanical behavior of nanomaterials. As I told you, mechanical behavior is a vast subject, and we are only discussing a very small part of it regarding the nanomaterials. That's about the strength. But you know, there are other aspects like ductility, toughness, and even the motion of defects inside the nanomaterials, or even you have superplasticity, and there are other aspects also. It's not possible to discuss all of them in one go. So therefore, it's a part of the basic understanding of the subject. We are taking only the strength. And what we did in the last lecture is basically we talked about that only. We talked about the material properties which are decided by the application of the force or the stress. And finally, I showed you how to derive Hall-Page equation, which relates the grain size or the crystalline size with the strength of the material, especially the yield strength of the material. So first let us have some recap. Okay, the first and foremost important thing is that in the polycrystalline nanostructure materials or multi-layer materials, the strength provided by the grain boundaries are mainly dictated by two things. One, the generation of dislocations or the defects in the grain or the boundaries basically, and then pile up of this dislocation or defects in the boundaries so that the grain boundaries can act as obstacle to the motion of dislocation. This can happen in a multi-layer structure also. That's what's shown here on this example. In a multi-layer structure where you have two different kinds of materials deposited on top of each other with certain wavelengths of this structure, these dislocations which are generated at one boundary can have difficulty in moving across the boundary and reach the other layer, because the materials are different, the crystalline structure may be different, and so on. Hence, these boundaries can act as an obstacle to the motion of dislocations. And this leads to what is known as again boundary strengthening. Okay? And this we have discussed a lot. This is what is known as grain boundary strengthening. Okay, so grain boundaries can be used as a mechanism or as a ploy to strengthen the material, and that's why the nanostructure material comes into picture, where you can reduce the grain size drastically small enough to have a very high strength. And but you know, as I have shown you at the end of the last lecture, this doesn't seem to be happening for the grain size which are going down to below 5 nanometers or so. And what you see is rather an opposite effect. What is that? We do see a grain boundaries acting as a softening agent for the material. What does it mean? That means if you reduce the grain size to a very small one, grain boundaries will no longer can be used as a strengthening agent, but material strength will go down. And that is what is known as a Hall-Page softening or grain boundary softening, or breakdown of grain boundary, breakdown of the Hall-Page equation. Okay, this is known as a grain boundary softening or Hall-Page softening, because Hall-Page is the relationship which dictates how grain boundary, grain size relates the yield strength of the material or hardness of the material. So the basic model is basically known as a dislocation pile-up model of the grain boundaries. Dislocation generated from one grain boundary reaches the other grain boundary and gets piled up, and that leads to strength. Well, before we discuss, we also discussed about, we are mostly interested in plastic portion of the stress strain curve, right? We are not interested in the elastic portion. Why? Because the yield strength is which demarcates the plastic and the elastic portion of the stress strain curve. So therefore, any kind of strengthening happening in the elastic portion is not, we are not interested. Okay. We are mostly interested in the plastic region of this stress strain curve. That is what is known as the flow curve. And normally flow curve is given by the equation sigma equal to k epsilon to the power n, where sigma is the true stress, epsilon is true strain, k is known as the strength coefficient, and n is popularly known as the strain hardening exponent. Okay. So, that means this relationship basically governs the stress strain behavior in the plastic part of the flow curve or plastic part of the stress strain curve in a very, very nice manner. The important parameters which are basically decided by the material is k and n, and remember n is an exponent, normally it is less than 1. So, therefore, it is a fraction, okay. And hence this relationship, which is a relationship between sigma and epsilon, is too much dependent on these parameter n, okay, because n value changing will lead to significant change in the flow curve. So, therefore, you must remember that we can always determine the value of n by simply taking a log on the both sides. That is what is shown on this derivation. I did it in the last lecture, and it is very clear the slope of the curve of log sigma versus log epsilon provides you the value of n, and n is very basic material property. Well, most of the cases you may not be able to measure these tensile properties of material because of the sample size limitation, because of the accessibility to the tensile testing machine. So, in those cases we use hardness as a parameter for any kind of obtainment of the mechanical properties, mostly the strength, right. As you know, hardness is nothing but resistance to permanent indentation or deformation, okay. And it means that any resistance to scratching on the wire is related to hardness. Most tooling used in manufacturing must be hard for scratch and wear resistance. Think of your serving blade, it must be scratch and wear resistant, because you are using it to cut something which requires it to be retain a sharp edge, and if it gets blunt because of the scratch or wear, then it does not serve the purpose. So, there are many such things which are used day to day life that needs to be hard, and therefore hardness is used as a measure of strength, a measure of scratch and wear resistance, we can say. Well, this resistance to permanent deformation is related to the line defects or defects, rather movement of defects in the material, and most important defects are the line defects, okay. And line defects is nothing but a dislocation, okay. And dislocation can be viewed, the motion of dislocation is viewed as a rug with a fold. When you are using a carpet, if you have a rug and you give a light tapping on the carpet, that rug moves slowly with the fold, right. And this is because it is easy to move it over the carpet without much application of force. Something is true for caterpillar. Caterpillar movement can be easily thought of same as like a dislocation moving in a material. How it is done? Well, that is very simple. Caterpillar moves in a small part. It does not move the whole body like us. When you walk, we walk in a whole body, right? But caterpillar moves only a small part of it, and then that movement is transmitted from one part of the body to the other part of the body. So, the whole process leads to a finite displacement. As you can see, from here to there, the finite displacement is possible simply by making a fold in his body. So, that is something, that is how the dislocation actually moves in a material, and that is obvious because this motion requires very low, much lower energy than breaking the bond altogether in the material. Fine. So, dislocation can be edge or screw depending on how they are oriented in the edge. Dislocation plane and the extra half plane, they are perpendicular to each other, and the screw, they are parallel to each other. That we have been discussing a lot, and if you have problems understanding it, we can always discuss during our discussion periods, or I can even refer some books so that you can understand. But as some of you are not from the metallurgy or material science background, you may need to work a little bit harder to understand this aspect, and this is true for others also. Well, dislocation motion in the material happens by small segment. That's basically known as a Berger vector, and as the dislocation moves from one part of the crystal to the other part of the crystal, it leads to a step on the surface, and that's nothing but a slip step. Okay, and remember, dislocation can move only on a slip plane; it cannot move on any other plane. So therefore, these slip planes are basically the closest back planes in a material. In FCC, it's a 1-1-1 plane. How do you see dislocations? You can be easily seen using transmission electron microscope. They are actually nanoscale objects. They look like a line or a curve in the transmission electron microscope. And this is dislocations in titanium and silicon. You can also have dislocation in ceramics like aluminum oxide or titanium carbide. And so they also look like a line or curve. They're similar, but remember, the plasticity is because of the dislocation motion. Dislocation generation and motion. Only when these two things happens, then only you can get some amount of plasticity. Otherwise, material breaks down like a brittle manner. Like you see a glass. If you throw a strain of glass, windshield or any glass, it breaks down very easily. So that's no signature of plasticity at all in that kind of situations. But on the contrary, most of the metals and many ceramics do show plastic deformations, and that's why actually these aspects comes into picture. Whole page equation will be valid for those materials only. If you cannot generate dislocations, there will be no pile up, there will be nothing like a Hall page. Well, as I said, dislocation can be generated from the gain boundaries, because gain boundaries, as we have discussed a lot in our previous lectures, they have some kind of a lower order elements of the atoms or disordered elements of atoms, not perfectly disordered, but it's kind of a disordered element of atoms as compared to the grains, and therefore they can actually act as a source for dislocation generation, or otherwise you can have a frank reed source. That also possible inside a grain. Both are possible. So gain boundaries can act as a source of dislocation or the frank reed source. Nonetheless, and as the dislocation generated, they move through the crystal and then go away. And once they go away, then once they move inside the crystal, obviously they are moving, and sometime again they will also come in a contact, or rather face-to-face contact with another gain boundary. Okay, so very simple. You have a grain like this, and dislocation generated from this gain boundary. They just move. You can see that, and then reach this gain boundary, and there they will find it's an obstacle present to cross over or to cut over, and that's why they cannot move. Okay. So that means what? Dislocations can be piled up if there is a gain boundary in front of them. So you must be thinking, side is telling one side dislocation generated from the gain boundary, other side dislocations are getting piled up the gain boundaries. Okay, that's very simple. See, if you think of two grains like this, the fact that there are two grains, the crystalline planes are not parallel to each other. That's why their orientations are different. That's why they are called two grains, right? So now, if this is the slip plane on which dislocation is moving in this grain 1, okay. Obviously, on the grain 2, the same plane will not parallel. So same plane will unlikely to be parallel. So dislocation cannot easily move across from one grain to other grain because of these aspects. Because dislocation, as I said, can only move on the slip planes. Fact that the slip planes are not parallel from one grain to other grain, they cannot cross over or move. Am I clear? So that's what actually makes the gain boundaries as an obstacle, and then dislocation gets piled up. So as the dislocation gets piled up, we have discussed a lot, given an analogy to the railway ticket counters, right? You could have seen that people standing in front of ticket counter buying tickets, making a queue, and this is something like a pile up of a human standing in front of a ticket counter of a railway station, okay? And that means what? Then when that happens, if there is a movement of one of the persons actually standing in that queue to the back directions, not in the front directions, there will be kind of a force acting on the person standing nearby. and this will percolate, or this will slowly move forward, or move actually from one to other, and then there will be back stress created. Okay, some kind of force acting on that. Okay, that is what you can clearly see, and this back stress is basically creates strengthening. So back stress then makes the other dislocation coming over difficult. Why? Because these dislocations which are actually following, like this one, they need to cross higher amount of stress in addition to the stress required to move on the plane, right? Because the back stress is going to add up to these force against the motion of dislocations. Okay, so that's how actually gain boundaries acts as an obstacle by providing this back stress, right? So it has a resolved shear stress which is making the dislocation to move on the slip plane, right? And back stress is stopping them, or basically forcing them not to move on the dislocations, and therefore they need to cross over, or they need not cross over, I'd say, or they need to be pushed by additional forces which is equal to the back stress plus the resolved shear stress. Okay, and that is leading to the strengthening of the material, right? So the extra force is extra strength. That is how it can be correlated, correct? Well, if I consider only the two gain model which I discussed the last time, and as we say, these are two gains. In the first gain, dislocations are moving on a slip plane because of the application of shear force tau s, and that's nothing but critical resolved shear stress, right? That is by tau s, and this allows the dislocation to move on the slip plane and reach the gain boundary. Once the gain boundary reaches, the slip planes are not parallel to each other, so therefore this dislocation cannot simply move across the gain boundary and then move on the slip plane on the other side of the grain. It's not possible, and because of these aspects, they started piling up. Because they cannot go, that's why they cannot pile up. Think of a bus in which the people want to go inside the bus, okay, but the doors are closed, right? So what will happen? They will pile up in front of the doors. But as soon as the door is open, all the passengers will go inside the bus, the pile up is over. That is something like as soon as the slip planes are parallel, the dislocation can easily move from one gain to other gain, right? So that's very odd situation, which is very unlikely to happen in a normal grain structure materials, because grains have different orientations. Am I clear? So the central idea is that dislocations are forced to pile up at the gain boundaries, either because there is a barrier to cross over into the next grain, or because source must be activated in the grains. You understand that? These are the two important things you want to understand. First is the barrier to crossover. What is the barrier to crossover? Barrier is nothing but the slip planes are not parallel. That's why. Or it needs to activate this, source in the other grain. Okay. Whatever the slip plane is, see, FCC crystals most important slip plane is 111, because that is what is the closest back plane. Am I right? But dislocations can also move on 100 or 110 planes also. Those planes require higher critical resolved shear stress. Am I clear? So suppose this grain, which on the dislocation moving is nicely oriented, and dislocation moving on 111 plane. But on the other hand, right, the gain 2, that's not the case, right? So what gain 2 probably the plane is 110. So in order to start the dislocation motion, or dislocation rather movement process in the other grain, you need to create a source on 110 plane. That's because more stress. The critical resolved shear stress to move a dislocation on a 110 plane is much higher than 111 plane, because 110 plane is not the closest back plane in FCC crystal. Am I clear? So these are the two important barriers, or two important aspects which leads to the pile up of gain dislocation at the gain boundaries. That's something you should understand very well. Okay, and that is the main reason the gain boundaries acts as a strengthening agent. Correct. Well, classical explanation to Hall page effect is that some stress concentration in a given grain is required to initiate the slip in the neighboring grain. I have listed it down, taken from internet literature. Okay, so this is what is the classical explanation for the Hall page effect. that you need some kind of stress concentration in a particular given grain to initiate the slip process in the neighboring grain. The stress concentration is most possibly obtained by dislocation pileup, which is shown here in this picture 5.5 taken from the book of Courtney. Okay. The stress essence of the argument is that stress is higher as the number of dislocation increases. Thus, the larger the grain size, more quickly is the critical stage is reached after the slip is initiated in the neighboring grain. That is obvious, correct. The form of the equations describing the pileup is contain a term root d or root d by r rather, or the grain is the grain diameter, r is the distance to the source in the neighboring grain from the boundary. Okay. Fine, forget about r, but it is basically proportional to root d, 1 by d actually, where the formation of equation. Okay. The pileup stress is basically proportional to root d, that is very clear, right. So, larger the grain size, more quickly in terms of macroscopic strain, the critical stress reached at which slip is initiated to the next. Okay. What does it mean? That means if the grain is bigger, you need less stress to start the dislocation activity in the next grain. As the grain becomes smaller, you need more stress to start the dislocation activity in the next grain. That is how actually this can happen. Or other way, as the grain size becomes smaller, you have more grain bound radius, so more obstacle to the resolution motions, and that also can provide to strengthening. So, you can understand that there are two aspects of that, and this is what I showed you in a bulk nanostructure material. You have so many large number of grains, small size nanostructure grains, and with a very large grain boundaries. So, therefore, dislocation find more difficulties in moving from one grain to other grain. This is again shown here also. I am not going back into this. Well, so then I discussed about these Hall page equation, which I will not go back again, only to tell you that the way we can think mathematically is this, that grain boundary acting as a barrier to dislocation motion. So, therefore, we can think about the barrier as a certain strength, and that strength can be F star, that is the critical strength required to be crossed over. Now, obstacle can be overcome only when number of dislocation multiplied the Baader vector, that is the total displacement, into the critical reserve of stress, that is this not critical, that is the shear stress required for this process, the tau minus tau 0 greater than this obstacle, value of obstacle. Okay. Now, n can also be related with these things by size of the grain and many other things like Poisson ratio, vector. I have already discussed all the shear modulus G, and then we can do a mathematical analysis and found out that the sigma is equal to sigma 0 plus k star divided by d to the power half, and that is the classical Hall page equations, and in which case star is 10 coefficients which can have value between 5 to 15 GPa, and sigma 0 is the constant value. So, sigma is here is the yield strength. So, you can see yield strength is directly proportional to d to the power minus half, or it is inversely proportional to root d, whatever you can take about it. And this is what is the thing which I discussed in the beginning of the lecture and telling you again and again so that you do not forget. Well, K has values in gigapascal or milli or the mega, this is mega Newton per meter to the power 3 by 2. Okay. That is what it is. This is taken from the book of J.D. Embury, Strengthening Methods in Crystals, and many others. Kelly and Johnson, or maybe some other papers also written here. As you can see, BCCH3 metals has very high values of K. Well, one can, this is taken from Pech equation 1953, Pech original paper, and now you can clearly see the dependence of brittle fracture stress on the grain size at 77 Kelvin, and you can clearly see that for the mild steel, ingot iron and the spectrographic iron, all of them fall on one line, and sigma versus d to the power minus half. That also tells us that this equation is very nicely can describe the whole behavior of the grain size dependence on this strength. Well, but then in those days there was no concept of grain, nanocrystalline grains like 1953. although they are there, but people didn't know about it. Okay. And so once we could prepare the materials with nanocrystalline grains, then start measuring it, and people have seen, or many researchers have seen, the strength can increase sometime 3 to 4 orders of magnitude. Okay, you can clearly see that 1 becomes 3 or 4. See, it becomes triple or even 4 times. Okay, not order of magnitude, but times actually. So therefore, from 50 nanometers to about 10 nanometers, I have a drastic increase of the hardness. That's possible for this is nanocrystalline copper. Same thing has been observed for nanocrystalline copper, but okay, once you decrease the grain size further, as you can clearly see that below a certain grain size of 10 nanometers or so, the strength started going down or rather than remaining constant. It doesn't increase much, and that's why the breakdown of the Hall-Page equations happens. This is what it is. The Hall-Page equation started breaking down. So you must be thinking, why does it happen? Then we will discuss about that. Same thing happens for nanocrystalline nickel, and you can clearly see here also it's shown very nicely the breakdown of Hall-Page equation. Okay, and there also I am showing you for multilayers. So how does it Hall-Page equation breaks down? Okay, that's very simple to understand. And as you see, I'll go back to this picture and explain. Okay, remember this picture, yes. As you see in this picture, as the grain size decreases, only fewer number of dislocations can be packed in the pileup, right? So I draw last time also, I'm drawing again. If I reduce the grain size, so here you can have many dislocations can pile up, but there it is getting reduced further, right? So what do you see? From here to there, then to there, the fewer number of dislocations can be packed in the pileup, right? So if lower is obviously then lower is the magnifying effect. If you have more pileup, more is the back stress. Lower is the pileup, lower is the back stress, right? So therefore, applied stress will also be required to be less to cross the obstacle, and there comes a point that n, which I derived in the last class, n become 1. So no pileup is possible, right? So now you know that n is equal to what? N is equal to C d sigma minus sigma 0. Go back to my derivation, e to the power e equal to b. That's equal to 1. So I can easily write, okay, C d sigma minus sigma 0 is equal to EB, right? That's one aspect. Second thing is this, okay, let me erase this part and do it for you. Second thing is this, that we know that Hall-Page equation, right? What is the Hall-Page equation we know? Okay, we know very easily that in case of Hall-Page equation, what do I know? We know sigma minus sigma 0 is equal to k star or k dash, okay, to the power into, I think I have done that, k star b by d to the power half, right? So let us put down this sigma minus sigma 0 value here, right? So EB CD, remember D is the grain size, C is a constant, E is the elastic modulus, and B is the Barger vector, right? So if you do the mass properly, what do you get? You can clearly see D by B will be equal to E Ck star to the power square, right? So therefore, this equation will break down when this inequality will be applied. It tells you that D, which is the grain size, divided by the Barger vector must be less than elastic modulus divided by the constant C multiplied by K star. K star is also a constant, you know, right? And you know the value of K star. What is the value of K star? Okay, K star can be written here. K star is equal to 2, F star is the obstacle, E CB to the power half. So the K star is dependent on obstacle strength, elastic modulus, and the Barger vector. Constant C is obviously fixed per particular material, right? So that's it. So that means you know, when this condition is satisfied, the Hall page equation will break down. That's very simple way of thinking is that if you have only one dislocation inside a grain, there is no pile up. So there is no gain boundary strengthening. If there is no pile up, there is no back stress, there is no gain boundary strengthening. That's why the Hall page equation breaks down below a certain grain size. Am I clear? That's very something which is you should always remember. This is the reason actually Hall page equation breaks down. Okay, so from big grain, very big grain. Okay, let me just redraw this picture. I think I have drawn it pretty big. Okay, let me redraw it again. Like this, you have many dislocation pile up, gradually decreasing. Then you have only one dislocation possible to be accommodated. And that's why this breakdown of Hall page happens. And that's why this equation d by b less than equal to E by ck star square whole square is happening. And you must remember these aspects. Okay, so that's something which you have probably understood. I don't know, this is taken from a paper in Nature, 1998. You can clearly see this is basically hardness, and you know, for gain size more than 20 nanometer, less than 20 nanometer, for I think gold, and you can clearly see the Hall page and the Hall page inverse, both are possible. Hall page obviously tells you that strength is increasing as the d to the power half minus half is increasing, right? But then you reach a critical here. Here you can see there's a critical point below the strength is further decreasing. And this happens below about 20 nanometers, okay? And they say it's basically gain bound is to migrate, but no, basically the mechanism is same what I discussed just now. Below 20 nanometers, you can no longer accommodate more than one dislocation. So pile up is no longer possible, and that's how they get this effect breaks down. Well, now it brings us to a very interesting thing. Okay, what is that? So that means what? If you keep on decreasing the grain size, you have seen the strength is not increasing, right? There's a point below which the strength decreases. Now, if you still further decrease the grain size, what will happen? What will happen? Have you ever thought about it or not? Suppose that crystal size shrinks further until it becomes atomic dimensions. What does it mean? Until it becomes 1 nanometer size or so. This is a question some of you have already been asking me. So if I decrease the crystalline size further, 5, 10, 5, 2 and 1 nanometer, correct? So material now will be completely disordered. Okay, what does it mean? So this is a nanocrystalline structure, right? In which you have order arrangements of the grain, atoms in the grains and disorder arrangement of atom in the boundaries. So we have discussed a lot, right? Now, if you decrease the grain size too much smaller atomic dimensions, the grain boundary area will be very large, and all the structure will be completely disordered. And you know, many amorphous materials are there. Glass, window glass is amorphous material. Okay, ordinary glass, what you call, correct? Even you have metallic, ceramic, other ceramic materials which are glass. Polymer materials are also glass are present, correct? Among them are the polycarbonate, acrylic or plexiglass or polystyrene, which is used as one of the material for dress materials. The Barger vector of dislocations cannot be defined even in an amorphous material, right? So let us think of polymers. Okay, you know, polymers can be partially order or disorder, and you know, many polymers are there. You know, small crystalline regions in the disorder matrix, or you can also have polymers which completely disorder. So this thing, the concept which I'm talking about, it's also valid in those kind of things also. Now, you know, when dislocations cannot be thought about it, because dislocations are only, the concept of dislocation is only valid for order arrangement of atoms, because you're thinking of a slip plane, extra plane, movement of these dislocations. That's only possible when you have a completely odd arrangement of atoms. In a disordered arrangement of atom like amorphous structure, you cannot think of a dislocations. Okay, dislocation concept will no longer be valid. So in such a situations, material has extreme high strength. You can't believe it. Strength can go even farther. If you decrease the grain size and make it amorphous, it can reach even 5-6 times of the normal material. And people have seen it. But that increase of strength comes at the cost of ductility. Ductility and the fracture toughness reduces substantially if you are increasing the strength by this way. So, Michael Ashby, whose book is this, has given some charts. Okay, here is one of those. There are many charts actually given in his book, and there's a book by him. I told you, the design of material, mechanical design of materials, in which he talked about different kinds of charts to segregate the materials depending on the type of properties you are looking at. One of the properties which is important, yield strength versus density. And you can clearly see most of the polymers will be on the left side because they are low strength, low density, right? And then comes the natural materials, then you have metals, ceramics, and also as composites. So metals has always high density compared to ceramics and polymers, so they will be on the, but metal also has high strength, correct? Now what happens to nanostructured materials? That's what happens. If you make the same plot for different nanostructured materials, like here, you can see these are the nanowires of gold, silver, and copper, and then you have nanocrystalline metals. Here you can see here. Then you have ceramics, nanocomposites, even CNT composites. So you can clearly see still the nanowires wins over the others. Nanowires can have yield strength of the order of 10,000 MPa, that is 10 GPa. Okay, that's very classical. Well, why it's so, that's because separate discussions. But forget about nanowires. Even if you think of normal nanocrystalline materials, you can look at the yield strength of 1 GPa. Normally steel has a yield strength of 200 MPa or 250 MPa or maybe 300, correct? So we are talking about 1 GPa, 4 times higher than that. That's something which is very, very significantly high. So you can also have ceramic nanocomposites having such a kind of high strength with a density of about 10 or so, correct? So that means what? By making nanocrystalline materials, we can increase the strength further. Amorphous ones will be much higher. They will be close to this nanowires designs or even much higher, something like about 10 to 15 GPa. Okay, many of these materials have such a kind of high yield strength. At least I know about metallic glasses which can go up to 5 to 6 GPa yield strength. That is pretty large, but then you have very limited ductility. It fails miserably. On the other hand, these nanocrystalline metals may not fail miserably. They will have certain amount of ductility which can be used. Okay, so that's something which you must remember. So this winds up our discussions on the mechanical behavior of material. So we're going to start a new chapter, or new topics rather, not chapter. That's on the thermal properties. Okay, what do you mean by thermal properties? Mechanical properties, you understand, you apply force, how the material behaves. Thermal properties, obviously, if you increase the temperature, decrease the temperature, how the material behaves. That's something which is very important. So as you know, there are various kinds of thermal properties which are important in the material. Okay, and Ashby's book, they start with melting temperature and then go to thermal transports and many aspects of that, mostly these two. And in the book of Volat, there will be some aspects of thermal conductivity and other things are discussed. So we are going to discuss or limit our discussion to these aspects, because as I said, this course is of 1 semester long. So if I start discussing about one subject for long, then what will happen? I'll miss out some other things, which many of you may not like it. Okay. So when you talk about thermal properties, the most important thing we talk about is the melting temperature of material, right? Why it is important? Because the application temperature must be lower than the melting temperature of material any time you are thinking of using a material, right? That's something which is always will be true. Am I clear? If you want to use it in the aero engine, which burns the fuel at about 1200 degrees Celsius temperature, the application temperature or the melting temperature of the material must be higher than that. Otherwise, the material will melt down and then everything will be gone. So now question is this: if I decrease the grain size of the material, what happens to melting temperature? Does it increase or decrease? This is the question which we are going to answer, right? So in the bulk system, surface to volume ratio is small, the curvature of the surface is negligible, we have seen that. So therefore, for a solid in the bulk form, surface effects are always neglected, you never consider. On the other hand, in case of nanoscale solid, for which the surface to volume ratio is very large, and therefore you can no longer ignore the aspects of these surfaces. Okay. In addition, for the 0D and 1D nanomaterials, the curvature is also an important aspect. You have very strong effects of curvature on the material behavior, right? So consequently, nanomaterials, the melting temperature is size dependent. Correct? You understand that? So in nanomaterial, melting temperature will be very much size dependent. Well, by the way, how does the melting temperature dictated? Well, this is dictated by the equilibrium. Correct. So if I for a pure metal, suppose if I plot G, or free energy versus temperature for any pure material, okay, like you can talk about pure water, pure iron, or maybe pure titanium, pure polyethylene, okay, it's single component. So you know that G versus X curve, G versus temperature curves will have, okay, you know that, right? G is equal to H minus Ts, and if you do dG, finally you get VdP minus TdS, right? So del G by del T at constant pressure is equal to minus del G by del T as constant pressure is what? It will be entropy, right? That's what will happen. It's del G by del P at constant temperature is will be volume. Correct? So that means what? That means very simply that the slope of this curve G versus T will be negative, because entropy is always positive. S is the entropy. Entropy is always positive. It cannot be negative, right? So because there is a negative sign, it has to be negative slope. So that's why most of the cases they go down like this. Okay, let me just draw it properly and show you. This is a very important concept which you know very well. So suppose this is the free energy for the liquid phase of the pure material. Let's suppose this is free energy for water, liquid water. So what will happen to the free energy of the solid ice? Let me just draw using a different color. Obviously, below the melting temperature, free energy of the solid will be lower. Above the melting temperature, free energy of the solid will be higher. And let us suppose this is solid. And therefore, you can see here, this is the crossover point. This is the crossover point. That's why the free energy of the two phases are equal. This must be melting temperature, because at the melting temperature, at T equal to Tm, G of liquid phase must be G of solid phase. Then only they will coexist. Otherwise, why they will coexist? At 0 degree Celsius temperature, both ice and water exist. So this is the most important fact. But below this, that means this is T less than Tm. Below this, you can see the GL, L for the liquid, for the solid. I'm making a mistake. This for the solid. For the solid, the free energy is lower than the liquid. You can see that, no? So this kind of curves tells you relative disposition of the free energy curves, and that tells you relative stability of the free energies. And on this side, okay, this is T greater than Tm, liquid has a lower free energy than the solid. Correct? Am I clear? So therefore, in a bulk material, this is what happens. Because in the bulk material, free energy is given by this. We don't consider any surface energy effects, because surfaces are neglected. But as you know, for a nanocrystalline material, G total, I already told you, is G bulk plus G surface, right? This must be the case. You can no longer ignore. So then, delta G total change. Change is very important, right? Change is this. So this is the change here, correct? Or this is the change here. Change means difference, difference from one to other. That's what is change. So delta G total is nothing but delta G bulk plus delta G surface, right? So what is delta G bulk? You know that? You don't know. Well, that's okay. If you don't know, that's no problem. Delta G bulk can be easily calculated. Okay, let me just tell you. Delta G is from this equation. Okay, all right. All right. Let us start from the beginning. So G is H minus Ts. Okay, and then dG is equal to dH minus T ds at constant temperature, correct? Now, at the melting temperature at T equal to Tm, both have similar free energies, solid and liquid are same actually. So, therefore, dG is 0. So, therefore, dH is equal to dH minus Tm ds is 0, right? So, what I can write? I can write down that ds is equal to dH by Tm, or delta S is equal to delta H by Tm. And what is delta H? Delta H is nothing but latent heat for the melting. So, you can get delta S is as Tm. Now, I can write down then delta G bulk is equal to delta H bulk minus T delta S bulk, right. So, this I know, this is equal to L and this is equal to T, and this delta S is equal to L by Tm, right. So, I can then get a value of this. What will be the thing? Okay, let me just erase this part. I hope you have taken down. So, delta G bulk is equal to L 1 minus T by Tm, or many times people write delta G is Tm minus T by Tm, that is equal to L delta T by Tm. Delta T is the undercooling. So, you can see this is actually an approximation, this is not exactly true. That is okay, that approximation is good enough. So, that means I know what is delta G bulk, and you all know what is delta G surface. I will stop here, we will come back from this expression in the next class, okay, from these aspects, how in pure materials we can correlate the change of melting temperature or melting temperature function of size. We will come back to it. Thank you.